So with kind of going through these practice exam, right? I really want to focus on being able to hold on, set up the problem the right way, right? Because the setup is the most important part. So all these questions pretty much all have, let me just make sure. I would say two and one and two. I have an idea to where if you go about it the same way, like you still want to make sure that you're like kind of setting it up to where you at least have a picture, at least a free body diagram, right? So even when we look at this, right? We have a football workout, and they said it's a two linemen just pushing each other in a sled, right? And then their combined mass is blah 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 blah, and then the coefficient of friction, all that, these numbers, right? So we want to find the force applied to the sled by the lineman. So first things first is take that first line, right? These two linemen are pushing the coach on the sled. So what does that even look like? Let's try to do our best impersonation of drawing this. So you got two linemen, and they pushing on a sled their coach, right? Now this total mass is 300 kilograms, all three of them. So let's just say they're pushing the coach this way, right? They're pushing the coach this way. If I was to draw a free body diagram to simulate this, we already know the weight is down, so we have F grav. And then that's because they're on the ground connected, we have a normal force, right? So those are my two right there. So we are balanced in the vertical. Now, really, we're moving in the horizontal, right? And we even know that we have acceleration because they give us the word keyword right here, acceleration. So I know that this force applied is somewhere over here, right? But they tell us about this coefficient of friction between the sled and the grass, which makes sense that you're pushing around, you're gonna have some type of friction, right? So when I look at it, if I'm moving accelerating at a rate of 0.58 meters per second square, I'm gonna assume that my force applied from the push is gonna be more than my force of friction because Newton's second law, Newton's first law, an object in motion stays in motion unless acted upon by an unbalanced force. Now we have the unbalanced force, which is acting upon this object, which is the applied force. That unbalanced force is now created to where now we see some acceleration. So the unbalanced force, if the force is unbalanced on the object, then you see accelerations. That's what we have right here. So now we have our free body diagram. So now this is what we have to be able to set up the problem. And you can go about it pretty much setting up with Newton's second law. So we have a diagram, we have the free body diagram. Let me try and squeeze it in somewhere. This ends up being the second law problem. So we have a force. Some of the forces is equal to mass times acceleration. Now we just got to look at it from here, find the sum of the forces here, right? So if I was to repeat, let me kind of, yeah, I think I'm about to clear all of this. All right. So now we know we have a second law problem. So now we just drew it, right? We have acceleration. Which force in the unbalanced forces in the horizontal is going to be my winner? Which one is going to be my loser? As in, which force is a little bit bigger? Which one force is a little bit smaller? Would it be my applied force or would it be my force due to friction?
The applied force is going to be the winner.
So the applied force is going to be the winner. Good. So now I can set that up here, right? And then we have my loser would be the force due to friction, right? And that's equal to my mass times acceleration. So now once we get here, we pretty much got majority of the problem done. We can input our mass and then we can input our acceleration to now we find out what this value is. And then the frictional force we could find because the normal force, because now in the vertical we are forces are balanced. The sum of the forces is equal to 0, right? So that means that up equals down. So my normal force is equal to my weight due to gravity, which ends up being mass times gravity, the acceleration due to gravity, which you know is 9.8. So once you find this normal force, you can actually come back over here now and you can substitute because we know the frictional force is equal to mu times the normal force. Now we're in a situation where we're doing algebra. But it started off with that picture to visualize it, then getting the free body diagram, looking at some of the words highlighted here. Still in the same format, right? That given, assumed, and unknown, still in the same format here. So this is how you do set up the first problem. And then all you gotta do is plug in the numbers and just solve. So when you go home, well, after you're already home, but like over the weekend, play around with this, try and recreate this. I'll have the video up over the weekend. So if you want to play around with it, just go ahead and look at it and try to do this on your own. Any questions? All right. So I'll go to the next one. This is another good one, right? And we really want to be able to just go sit here and visualize this one, right? So we got a soccer ball and it's kicked horizontally at the top of a field house and it lands meters away from the field house. And we want to determine the height of the field house. So let's draw our scenario, right? We got the field house here. And we got a soccer ball. Right? Person kicks it. And it comes off. Boom. The distance of where it lands is 33.9 meters. We don't know the height, but we do know it comes off with a horizontal of 15.8. Right? So now this is pretty much going into understanding projectile motion, right? Well, understanding projectile motion, we have to realize that we both have motion going in our vertical and in our horizontal. I believe we have to set this up to where now we can use kinematic equations, but we have to lose it in both the X and the Y. So let me start off with what we want to find out, which would be, let's find out that height, right? So that technically that displacement, right? Use the third kinematic equation. I'm going kind of backwards. 1/2. And let's do it in the y first, right? So now when we get here, when we are given here, right? Now this one is the initial velocity, but in the x direction, horizontal. This also is displacement, but in the x direction. We need to find it in the y. So what would be the initial velocity in the y? Any guess? This is where we now start to assume.
Would it be 0?
Yes. It's 0. Because at the very first start, we are literally just like kind of like how we were in free fall starting at 0. And then we go. And then that's multiplied by the time, which we don't know. And then we got the 1/2. Now for this, because it's in the vertical, what would the acceleration be? This is another assumption.
9.8.
9.8
9.8 because it's what? The acceleration due to?
gravity.
Gravity. Good. So now we're here. So where if we recreate this, it's going to be just like we've seen before, the 4.9 delta t squared. So this is what we need to find our displacement, pretty much to find that height, right? But we don't know what t is, right? But just with projectile motion, just as we have displacement going in we're moving along in our y, we have something going in our horizontal, right? So we can use the same equation to find out what t is, right? But just in our x. So let's do that. Right? Now starting off here, right? Remember I said this was our initial velocity in our x. So instead of 0, we're going to put that here. Because horizontally, we start off with the initial speed that's not 0, right? But horizontally, do we have gravity in the horizontal or is it in the vertical?
It would just be in the vertical.
So therefore, what would our acceleration be in horizontal?
What's the name?
Or a better question, do we have acceleration horizontally?
No, so 0.
0, correct. So now you have 0 here. So this term goes away. And then from our given, we know that it lands 33.9 meters away. So that actually is this number over here. So now you get here, and all you have to do is 33.9 equals 15.8 times delta t. To find out what the time is, basically how long it takes to hit the ground. And then once you get that, you plug that back into the 4.9 times delta t squared for the y to find a displacement. So really to find the time which crosses between the same time of having the horizontal motion and the vertical motion, you just need to find that time value and you're fine. But just setting it up, draw the picture first, go through the givens, then you make your assumptions, and then once you make your assumptions, then you find the unknown, which is b the height. It's just to get you to set it up. Still go through the same process and set it up when you get back on your own. Any questions? Seeing as then I'll keep moving forward. Now, this one right here, right? Let me stop sharing. I'm gonna show the last one, but I'm gonna actually, because some people have done it already, right? And I want to show the last one. Because this student did a good job of doing it how I said, pretty much doing it on their own. But I just want to make just a minor change and see if we could talk about it. And it's not to single anybody out, but it's just to show an example instead of me just starting off from scratch. Because I think this is something that would definitely happen if it was a real exam. All right, can everyone see this right here? All right, good. So the question is suppose that a student pulls with two large forces, force 1 and force 2, in order to lift a 1 kilogram book by 2 cables. If the cables make a 1 degree angle with the horizontal, then what is the tension in the cable? So far what I see 2 cables. Sorry, yeah, 2 cables, 1 tension, 2 tensions, right? And then I see the value in the middle of the book, and I see the weight going down, right? So far we got it to, it looks all right. Now, then I see even an equation trying to say that the tensions will equal to the weight, right? All right, good. Now, does anybody have any comments of what they observed when it comes to this problem?
Don't the tensions need to be diagonal so we can calculate them like the photos with the picture hanging on the wall?
So I like that, yes. So with the tensions being diagonal, that also gets us to where we can represent it with that, like they say, that 1 degree angle, right? And just even thinking about it, right? If you're trying to hang something or even just lift something, right? Like how often are you really holding something horizontal? Just like completely horizontal on its sides. And even with that, it'd be very difficult because with the brass being little, it probably would still drop down to the middle in between them, right? So that's where we're still gonna even probably get that angle. So let's just redraw this diagram a little bit, right? So where we have the block in the middle, right? The book, 1 kilogram. Oh, sorry, that's disappearing. 1 kilogram, right? Still have the weight going down. But now let's just draw these at just a slight little angle. Right? Above the horizon. Now, when we do that, right? What happens when we draw it at a slight little angle? Can we just add the forces together to the weight just like this, how we did before?
Would we only do the vertical parts of them?
So you saying do the vertical parts, right? So for do the vertical parts, we have to find the what?
Um,
Do you remember what the word is called? Starts with a C.
mm,
It's a vector force, so that has both an individual
oh, Y component.
Y component, right? So it has an individual Y component and X component. Now you just said the vertical, right? Because now when we get over here, let me change the color. Each component makes up, when we add together, the resultant, right? So we got a F2 X and a F2 Y. We want this to hang, right? So that would mean we need to create an equilibrium state. So now when we do that, we have our up equals our down.
Do you need to go outside?
And so then that goes to where now we have our actual F2Y and our F1Y equal to our gravity. So that's what we're going for, right? Not just the whole tension in general, but actually the Y components. And if we think about it, right, there's two Y components, right? And we will assume that they both will be holding up an equal share of the book, right? So we can assume that if we add both of these together, they would be the same. So let's just call it FY. So now with us doing that, right, we can get here to where now we figure out what FY is. And it should be half of the weight. Sorry, 1/2 of the weight. So now once we figure that out, we can now pull out this whole triangle and solve for it, right? So where now we know that we're looking for 1/2 the weight to find the F tension, right? And we have our angle. Now, by judging off of this, we got to do some trigonometry, right? Out of all of these, right, we got sine, cosine, and then tangent. Which one will we use to solve to find out the tension?
Sine?
Sine. We're doing opposite over hypotenuse. So then you set it up, sine of the angle which they give you is equal to the opposite 1/2 times the weight all over F tension. And then once you just do a little bit of algebra, you'll be able to find the tension force here. Any questions on that one? The goal with this was to really just kind of set you up, and I hope you see how these all come together, right? So now in the first unit, we started talking about forces, right? Just understanding forces in general. This third unit now talks about vector components. So where we start thinking about things as having horizontal Y components in 2 dimensions, right? And then in this last unit, which is question 3, where we talk about it, we put them all together, understanding how things have individual components, and that creates the forces that we have. So that's why I put them all together to kind of give you this rundown. And so now, with all of that, you have a good basis to where now I wanted to kind of transition to show you guys what I want you to kind of do when it comes to these labs, right? So this week, I really kind of, especially like from now until next week, Wednesday, I really want you to play around with the labs, play around with the stuff. They shouldn't take too long, to where you could try and get a good grasp of what's going on for yourself. Hold on real quick. Let me just make sure that I got the right ones. Hold on. Forces in motion. So like this first one, right? I'm about to share my screen. This first one is just like a little tug of war, right? And when you go through the prompts, you have it. Hold on, let me see. Yes. So where you play around when you see the little tug of war, right? If I pause it, if I add one here. And you can see how it goes and how it's affected. So that's all we're doing, just playing around with the different forces here, right? So just play around with that one and go here. But that's just to really get you what forces. Now the next one, hold on. Sorry, I was on mute when I was speaking. You'll use this one twice, I think, for the free fall and a projectile lab. So this one is like to simulate the free fall motion, right? So just play around with this, follow the instructions that come on the lab. So this is what this one looks like, right? Sorry, no, I was uploading something. Give me, and I had to, because I realized I didn't upload lab 3. Now, let me pull that up. So if you were looking for lab 3, I apologize because it was not uploaded. I think somebody had told me that, but it's up there now. And now we have this one too, and we can start exploring the different types of vectors. So I want you to do this one too as well. Hold on, let me see. Oh. Playing all the different vectors, and then you see how you could add them. Right? Change how you look at them. The angles with them as well too. So this was the next one. This is lab 3. Almost done with the first 3 labs. So now we have one more, which would be lab 4. Okay, back to the projectile one. So the one that we just did with the projectile one. So now you go back to the projectile. But this one is like the data lab. So where you shoot it off. And you get a graph based off of it, right? Now, if you do a continuous, you want to see how it goes over time, right? and you're gonna measure it, and then notice and answer the questions that go along with it too. So all these stuff is all on Blackboard. But I wanted you to get a feel of pretty much how the labs are going to be and what they were like playing around with, because we covered all of the things, right? We covered free fall. The first lab's free fall. The second lab's forces. Then the next one's talking about vectors. And this one is talking about projectile motion. And why do we do all that? Because I want you now to get comfortable with being able to now create your own Python simulator, right? So if you go in and you see on lab 5, right, on Blackboard, it gives you a lab document and it's all these different prompts and things, and it starts talking about Python, right? It'll lead you to this website right here called GlowScript, where now you're pretty much for 3D analyzations for Python. Now, someone did already ask me, what does this have to do with physics, right? What I want you to get comfortable with is creating your own physics simulator, right? So the first lab walks you through of how to just make shapes. So here's our example. Oh, wait, let me find one that works. I've done this with multiple classes. Oh, that's a simulator. Hold on. I want to find one where it's just making the shapes, right? Here's one right here where you just make the shapes. So the first lab is going to get you comfortable with coding to where you can make different shapes, right? So if you do it right, it looks something like this, right? Even just as though it says error in the program, this is fine. I'm trying to see if somebody else did one where it actually got to move. Bless you. Let me see. Yes. You play around with it, you can actually get it to where you get some of these things to rotate, right? And now this is what the code looks like behind the scenes, right? This. So playing around with it, you could do it yourself, or what I'm going to tell you, which is put it in ChatGPT to be able to get it to work for you, right? But once you get that, the main thing that I want you to now work on is creating your own physics simulator. So here's a free fall simulator. So where now you can change the launch angle, the launch speed, and run the same program, right? So where now you can use your simulator to create a velocity and time graph and figure out what the launch speed and angle is going to be. So this is what a couple of people have used to create similar to that data lab we did, this projectile lab that we did earlier, right? It's the same type of thing. And then there's code behind this, right? Now, what I want you to do is once you get to this point, literally come over here, come to lab 5. Download this, right? Come to ChatGPT. And just upload it here. Now let's see what it comes up with. It says writes to full, right? No problem. Now this is a lot, right? Now if I come here, let's see how it does. By see, 2 seconds. And you can do the same thing for 6, right? I think I got one more upload. So this one comes up with 2 different codes, right? So here's a one dimension, right? So this is a free fall. I'm gonna do another one. There we go. Now, why did I have you do this? It's because I want you to learn how to be able to code, right? This is just a skill that's useful. How to use the AI tools to teach yourself it, right? Now, there's code inside in the back when you do to edit the program, right? Let ChatGPT give you at least a starter example and then just go backwards and try to understand it, right? What I want you to do is submit the code that you have onto Blackboard. So copy it, paste it, and send it as a comment, submit it so that I could just see it. So that I can run it myself and see what it came up with, because it comes up with something new every single time. But once you get the code, pretty much use it to be able to help you out to understand what's going on so that you can understand just a little bit how Python works and how you can use it in the future. Well, this is just for you to experiment and have fun with it, but also learning how you can create your own physics simulator. So run through the first 4 physics simulators to learn about the concept that we just did, and then come back and use 5 and 6 to be able to learn how to create your own physics simulator. And then also work on those, but then also to try to practice problems while you're at home. So this is enough to kind of wrap up the first, let's say, half of this course, to where we have went through everything from the beginning with kinematics to now that middle part where we start talking about forces and vector components, to now we can start talking about laws of conservation. So on Monday, we're going to definitely come through and we're going to be able to do the practice problems all together. And I'm going to just have you just sit down, same thing, just go through them. Hopefully you practice over the weekends and just go through them again, and we'll go over them. And then we'll start Monday too with unit 5, where we kind of go through and start talking about laws of conservation when it comes to momentum and energy, and then getting into solar stuff at 7. So April will be a lot to cover, but I think we'll do a good job of putting it all together. Any questions for me? Also, when it comes to the labs, right, I'm going to extend the deadline to about all the labs, let's say about 2 weeks. So I'm going to change the date for all of them, so they should be doing about 2 weeks. So let's say the 15th. And then I'll make the homework 3 and 4 do. Actually, I'll make everything. The homeworks, the labs, all do the 15th. So you have a full 2 weeks to work on everything while we learn this new material. Is that all right? All right, sounds good. So like I said, that is what I have for tonight. So I'm pretty much done. Told you we get out of here a little early. So you guys all have a nice night, and I'll see you on Monday.
Thank you.
Thank you, Professor.
No problem.